Howdy, howdy. This is Mr. Potter. In our class sessions, we've been talking about the relationship between antiderivatives and the areas under the curve. How if I know that f of x is an antiderivative of my function f of x dx, then we can find the area under the curve between x equals a and x equals b of our function. And it's simply just my function evaluated at my top value minus my function evaluated at my bottom value. This is that fundamental theorem of calculus that we've mentioned in class, and we'll be using it a little bit today. But I want to do is I want to talk about some more properties of definite integrals. But before I do that, I do want to talk about one quick thing. This has been mentioned in class a couple of times, but a lot of people get confused about the fact that we can have a negative definite integral. And this is confusing for some people because a definite integral is supposed to be area. And the question is, how can you have a negative area? Isn't area always positive? And the fact is that a value for area may be positive, but it may represent a quantity that is in fact negative. For example, let's say that I was to tell you that the velocity at a particular time was equal to 2 minus t. And I wanted to figure out what my position was from 1 to 4. Well, I'm looking at the graph of my function. This is v of t equals 2 minus t. So this is going to be a line with negative slope from 1 to 4. And what happens is I have an area that lies completely above the x-axis, and this is a positive area. But I also have an area that lies completely below the x-axis. And although the area itself is positive, that is true, that area cannot be negative. What it represents is a geometric sense of velocity times time divided by 2. Well, this represents displacement. And we know that displacement may be negative. And in fact, any time that I'm dealing with an area that lies below the x-axis, I'm really talking about a negative quantity, even though the area itself may be positive. So in this particular situation, I've got a triangle with a base of 1, a height of 1, and so this is a positive 1/2. But then I've got a triangle with a base of 2 and a height of 2, and so this ends up being a negative 2. And so my total displacement would be equal to 1/2 minus 2, or negative 3/2 units, whatever my distance units are. So I first wanted to touch upon this because we can have a negative definite integral. It is true that areas must be positive, but what's represented by a definite integral may be a negative expression. So I wanted to touch on that because we are going to be talking about properties of definite integrals. And there's some very basic properties that we have. First is if I'm talking about the definite integral from a to a of f of x dx, I know from the fundamental theorem of calculus this is supposed to be my antiderivative at a minus my antiderivative at a. And of course, if I'm subtracting the same quantity from itself, I should end up with 0. Of course, if I'm looking at it from a geometric perspective, I'm talking about the area under the curve from A to A. Well, there's no width here, and so this area has to be 0. So in any case, as long as I'm taking the definite integral from a value to itself of f of x dx, I'm always going to get 0, no matter what. And there are some other properties that we're going to be talking about with this as well. One property that we have is that if I want to find the definite integral from a to b of f of x dx, and I want to add it to the definite integral from b to c of f of x dx, I end up with the definite integral from a to c of f of x dx. And this also makes sense both ways, both in the purely geometric way and in the fundamental theorem of calculus way. Geometrically, I'm finding the area under my curve from A to B and adding it to the area from B to C. And so I end up with the total area of the curve from A to C. So geometrically, it makes sense. But from the fundamental theorem of calculus, I'm going to have big F of B minus big F of A. That's this first integral. And then for the second integral, I'm going to be adding big F of C minus big F of B. And I notice that these quantities here end up subtracting out. And so I'm left with my antiderivative at C minus my antiderivative at A. So the idea is that I could have two contiguous intervals and find the definite integral from one to the end point of the other. I'm really just adding those two areas together. Another one that's a little bit common sense is that if I know that my function f of x lies completely between c and d, in other words, if c is my minimum and d is my maximum, then I know that the integral from a to b of f of x dx must lie between c times b minus a and d times b minus a. And that makes sense if I think about it geometrically. The area under the curve from A to B, this area here must lie completely between the biggest possible rectangle that I could draw and the smallest possible rectangle I can draw. So these areas must lie in this order as well. I've got my largest rectangle here, I've got my smallest rectangle here, and my definite integral must be between this overestimate and this underestimate. And indeed, if I know that f of x is less than or equal to g of x on some domain from a to b, then I know that the integral from a to b of my function must lay less than or equal to the integral from a to b of g of x dx. And this just makes sense because if this has a higher y value, then the area under the curve should be more. But there's one other one that I want to talk about that's not as intuitive, but it's still very important to discuss. The idea that if I want to find the integral from a to b of f of x dx, this is going to be equal to the opposite of the integral from b to a of f of x dx. In other words, by exchanging these values, by changing the upper limit and lower limit, then I end up with the opposite value. And this is one of those situations where it makes sense from the concept of the antiderivative. Here I'm looking at f of b minus big F of a. And over here I'm looking at big F of A minus big F of B. And of course, it should be the opposite. But thinking about it from a geometric sense is a little tricky. If I want to think about this from a geometric sense, what I really want to do is I want to think about it as if I'm finding the area under the curve, then what I'm really doing is I'm looking at areas where these distances are going backwards. And so this idea of B minus A, these actually end up being negative bases. And because these bases have negative widths, and I'm adding up all of these negative widths, I really could factor that negative one completely out. So these are some of the properties that we have of definite integrals. The idea that I can take a look at these limits and actually come up with some interesting ideas about them. So I wanted to go through a few examples of this. So let's say that I tell you that the antiderivative from 1 to 4 of f of x dx is equal to 2. The antiderivative from 4 to 6 of f of x dx is equal to 8. And the antiderivative from 4 to 6 of g of x dx is equal to negative 3. And again, remember that even though the area can't be negative, this definite integral can represent a negative quantity. That's perfectly acceptable. So if I wanted to know what the integral from 1 to 6 of f of x dx was, what I would need to do is I would need to say, well, I know from 1 to 6 that's really from 1 to 4 plus from 4 to 6. So this should be the integral from 1 to 4 of f of x dx plus the integral from 4 to 6 of f of x dx. And so this should be 2 plus 8, which is 10. I could also ask what the integral from 6 to 1 is. And because it's just an exchange of these limits, it should be the opposite of this. So it should be negative 10. If I want to know the integral from 3 to 3 of g of x, so even though I don't know anything about g of x except what's happening between 4 and 6, because these values here are the same, I know that that integral should be 0. And one last thing that I could do is I could estimate the integral from 4 to 6 of f of x minus g of x dx. Because from the property of integrals, this should be the integral from 4 to 6 of f minus the integral from 4 to 6 of g, which would give me 8 minus a negative 3, or 11. So there are some things that I can do to look at these values, to compare different integrals and combine them. I can either combine them by combining their domains, or I can combine them by combining their ranges. But either way, I can evaluate these definite integrals, which is some limited information at the beginning. The other thing that I wanted to talk about is the mean value theorem. We've been discussing the mean value theorem throughout our calculus class. Remember, the mean value theorem says that f prime of c is equal to f of b minus f of a over b minus a, as long as f is continuous on a closed interval a, b, and differentiable on the open interval a, b. And as long as this is true, as long as f is continuous on the closed interval and differentiable on the open interval, then we're all good. But what if I have a situation where f is really the antiderivative of f of x dx? In other words, if I have some function who's going to be behaving as the antiderivative, well, if this is true, if my function f was continuous, then certainly the antiderivative must be continuous, because it's just the area of a continuous function. And from the fundamental theorem of calculus, the derivative of an antiderivative would be the function itself. So as long as f satisfies these, then my big F has to satisfy it as well. So in other words, big F prime of C must be equal to big F of B minus big F of A over B minus A. But if F, big F is the antiderivative of F, the derivative of that should be F of C. And this is 1 over B minus A times big F of B minus big F of A. That is the integral from A to B of f of x dx. So what I've got here is I've got the mean value theorem for integrals, but geometrically, what I'm talking about is that if I have a function and I'm trying to find the area under the curve from x equals a to x equals b, this area here has got to be equal to the area of some rectangle. This red rectangle has to have the same area, where this value here is the average value of my function. And so this brings up an interesting idea. This formula here allows us to find the average value of a function. So in other words, if I wanted to find the average y value, if I wanted to find the average height that this function reaches on a domain, I'm basically finding out what's the y value where this rectangle with a horizontal top has the same area as the area under the curve. And so it ends up being the integral from a to b divided by b minus a. In other words, the area divided by the base should give me the height. So I want to go through a couple of examples of that. Finding the average value of a function. So let's start with the square root of 9 minus x squared on the domain from negative 3 to 3. So on this domain, I know that I'm talking about half of a circle. Geometrically, what I'm talking about is a semicircle going from negative 3 to 3. And I know what the height is. The height here is 3. But I can also find the area of this. This area has to be equal to 1/2 pi r squared, or 9 pi over 2. But I also know that this base is 6. And so that means that there's got to be a rectangle with the same domain from negative 3 to 3 that has the same area as the area under this semicircle. And this height ends up being 1/6 of 9 pi over 2, or 3 pi over 4. So this is my average height of my function. Now I could have done this as well if I knew what the antiderivative from negative 3 3 of 9 minus x squared. The thing is, we've talked about this before, and there are some situations where taking the antiderivative analytically is very difficult. Sometimes the only time we can do these, or the simplest, most straightforward way we can find the area under the curve is by using a geometric formula. And that's why we learn those geometric formulas, because I have no idea what big F of B and big F of A are going to be here. But I know that if I take this 1 over B minus A times this integral, this is going to be my average value, which I know geometrically is 3 pi over 4. I can do this a little bit more analytically for this function. Let's say that I'm talking about y equals the sine of x on the domain from 0 to pi. So I know that on the domain from 0 to pi, my sine function is going to go up to a maximum value of 1 and then back to 0 at pi. But I know that there's got to be some rectangle of some height that has the exact same area as the area under this blue curve. And I know that the formula for that should be 1 over B minus A times the antiderivative from A to B of my function dx. Now I know that the antiderivative of sine is negative cosine, which I'm going to have to evaluate from x equals 0 to x equals pi. And then whatever I get from that, whatever value I get, I'm going to have to divide by pi. And so I'm going to have the negative cosine of pi minus the negative cosine of 0 over pi. Well, cosine of pi is negative 1, so this ends up being 1 minus a negative 1 over pi, or 2 over pi. And so that means that this average height of this rectangle is really 2 over pi. That's the average value of sine of x on the domain from 0 to pi. So we've talked about properties of antiderivatives, and we've talked about using the mean value theorem to find the average value of a function on a given domain. We'll be continuing to talk more about definite integrals the rest of this week. But thank you for watching. This is Mr. Potter. Have a great day.